Okay, so hi, I'm Alec, and I'm a PhD student here, and I'm going to be talking about kernel methods today. Just do the short version the second time. I don't know if anyone can see the laser. I'll just point. Okay, cool. So why do we care about kernels? Well, let me first talk about basic supervised learning problem or statistical model fitting. Okay, so for this case, we think of supervised learning as being interested in trying to find some parameter vector W to minimize some data-dependent function, and this function is quantifying the merit of our statistical model. Okay, so in order to be a little more specific here, we can think of we have a feature vector x and an output variable y, and we want to minimize some loss that depends on this data. Okay, so we define a loss function L that depends on x and y in our model parameter W, and we would like to minimize this function with respect to W. And this expectation is taken with respect to our random pair x and y. Okay, so this relates to our classical statistical model fitting case for the case that we have n IID realizations of this random pair x and y. We can rewrite this expectation here as a sum. So this can be representing, for example, maximum likelihood estimation. Or you can also formulate the problem of training a support vector machine classifier, or a logistic regressor, or a matrix completion problem in this particular form. Okay, great. So for this above formulation here, it only works for linear statistical models. Well, what do I mean by that? Well, we have some feature vector x, and from that feature vector we want to predict an output variable y. And so we're going to do that through an inner product. So for example, we have our parameter vector w, we take an inner product with x, and that is what we map directly to y. We could also, so this is for the case of regression, but for the case of classification, we just compute the sign of that inner product. And so that's what binary classification would be. And there's some pretty straightforward extensions to multi-class classification or higher dimensional regression, which sometimes people call generalized linear models. Okay, but what if instead of being interested in a linear statistical model, we're interested in a nonlinear statistical model? So instead of W transpose X, we just have Y equals f of X. What is f? Well, it's just some generic function. So it's a nonlinear classifier. Well, why would we try to do this? Well, here's a cartoon example of a horribly non-linearly separable classification problem. So if we were going to try to learn a statistical model of the form W transpose X for this kind of situation, well, we would get to, like, I don't know, 20% accuracy or something abysmal. So that would not be a good thing to do. And this kind of thing comes up frequently in, like, computer vision or more challenging data domains. Okay, so let's talk about function estimation instead of parameter estimation. How can we do this? Well, instead of having, let's go back to our loss here. Instead of having W here, let's just substitute in f of x. So that's all we're doing for this more generic stochastic optimization problem that now still depends on the random pair x and y. And for technical reasons, I've also introduced a regularizing function of our function. But this has a very similar flavor to the way we introduce regularization in normal statistical model fitting cases. Okay, so this looks pretty formidable. Actually, in general, it's intractable. So we need to assume that our function, which is in some hypothesized function class, we need to assume some structure about this function class in order to be able to handle this problem. Well, what can we do? Well, we can equip our function class h with a certain type of function called a reproducing kernel. And when we do that, that helps a lot. So let's do that. Let's equip h with a function with a reproducing kernel function kappa, which is defined on the product set of our feature space across our feature space, and it maps those that product set to the reals. So it behaves very much like an inner product. It's an inner product-like function. Okay, and this kernel has some particular properties. In particular, its Hilbert inner product, when evaluated at a particular feature vector with a generic function in the class, is just the original function evaluated at that feature vector. This first property is called the reproducing property of the kernel. It looks pretty funky to anyone who hasn't seen this before, but this is the source of the kernel trick that we frequently talk about in your machine learning course. So, for example, if you define some nonlinear transformation of your feature vector x as just being your kernel function evaluated at that x, notice that this second argument is blank. So this is a whole function, okay? But we never actually have to, in many practical applications, we never actually have to compute this phi of x. We only have to compute this phi of x inner product with another phi of x prime. So when we do that, actually, we can substitute the result into property 1 here, and then we just get the kernel function evaluated at two different feature vectors. So this is great. This is the kernel trick. That's 3 lectures in 1 minute. Property 2 here of this hypothesized function class says that h may be rewritten as the span, or the closure of the span of the kernel function evaluated at a feature vector. So what is this saying? This is just saying that our function class is defined by a coordinate system, and those coordinates are themselves the kernel map evaluated at the input space. Okay. So again, property 2 looks pretty exotic for those that haven't seen this before, but it's inspired by certain technical issues in functional analysis, and it allows a certain class of theorems called representation theorems to carry over into our function class h. So we'll get to that on the next slide, but just to make this a little bit concrete, here are a couple quick examples of kernel functions. So the Gaussian density, that's an everyday kernel. The other one, another popular one, is the polynomial, but there are many examples. For example, the sinc functions that come up in the analysis of band-limited signals and in signal processing, those are kernels. There are splines, Laplace kernels. There's a whole big bag of kernels out there, but we'll just focus on the Gaussian for today. Actually, all of the analysis is generic, but you can think of things as Gaussian because that's familiar. Okay, so now let's. That's like the space of our feature vectors. So you can think of it as our data domain. Yeah, it's a subset of our P. I'm going to be thinking of. So P is for parameter or whatever. We'll later clarify that X needs to be a compact subset of RP, but for now, you can just think of it as RP. Okay. So going back to going back to empirical risk minimization, where we substitute in our non-parametric decision variable, which is just a function. Well, now we're saying this function is in a function class equipped with this reproducing kernel. We mentioned that property 2 allows us to derive certain things called representation theorems. So for this case, we know the representation theorem says that the f star, the optimal function, which minimizes this empirical risk, takes the form of an expansion over kernel evaluations at the training set. So this is saying that the feature vectors evaluated the kernel map evaluated at the feature vectors in the training set form a basis for the function. So this is interesting. And so what does this buy us? Why do we care? Well, let's substitute in the representation we have by the representer theorem into the empirical min here. Well, when we do that, let's say there's a lot of pretty straightforward algebra, but what ends up happening is the optimization problem now is no longer over all of H, but it instead is over a vector of length capital N, where N is the number of samples in our training set. So that's interesting. It takes an infinite dimensional, functional optimization problem and pulls it down to a problem over Rn. So that's why we like representer theorem, because it makes kernel methods possible, or kernelized regression possible. Okay, so this is great, but note that here we're assuming n is finite. So for a particular example, this is just what kernel logistic regression looks like. So if we formulate like a particular probabilistic model, then you can formulate this as a functional optimization problem, which reduces to an optimization problem over Rn. Okay, so this is just to make it a little bit more tangible, but don't get too worried about the specifics. Okay, but unfortunately, when the sample size n goes to infinity, then if we define this kernel matrix as the gram matrix consisting of these, kernel evaluations at different elements of the training set, well, the kernel matrix parameterizes our nonlinear classifier. And as n goes to infinity, the size of the kernel matrix that parameterizes f is also going to infinity. This is a disaster. No computer has infinite memory. I don't care what Amazon Web Services says. They can't handle this. Okay. So henceforth, I'm going to be talking about the model order as the upper summoned index of f here. So note that in the empirical risk minimization case, this model order m is the same as n, but it doesn't necessarily need to be. This storage issue of the kernel matrix going to infinity, this is called the curse of kernelization. This is why people don't think kernel methods scale. I disagree, and here's why. Well, actually, before I get to that, I'll explain how people have tried to mitigate this memory explosion problem. Well, there are a few, let's say, there are roughly 3 categories of works that have tried to handle kernelized expected risk minimization. The first is a collection of works that doesn't seem too worried about the fact that the function f requires infinite memory to be stored. So they just try to analyze these, analyze an optimization algorithm without any regard for the fact that our decision variable, which is f, is blowing up. Okay, so they need to be referenced because they're, they motivated other works. Other works have just said, okay, well, let's just try to find a sparse approximation of the kernel matrix and the weight vector. So we can do that in a way that's independent of the optimization problem. Just try to find a low-dimensional representation and not worry about it if we're actually learning F star. Okay, so that's another group of works. Clearly, if we're actually interested in learning F star, then we need to tune our sparsification procedure to F star. So the most similar to what we're proposing are a few methods that have tried to do this, but still for the batch setting and only for special cases. So, for example, there have been some special cases for support vector machines and logistic regression in the online and offline settings, but no one's been too worried about the general expected risk with a convex loss. So that's our focus. And in contrast to these prior works, we don't fix the model order of the function, but we instead allow it to be tuned directly to what's necessary to derive a convergent optimization method in the Hilbert space. So that's the sort of quick summary of what we're doing, and the way in which we tune our sparsification procedure to the optimization sequence is by fixing some like error neighborhood around the sequence, and then trying to sparsify as much as possible while remaining in this error neighborhood. And through doing this, we're able to prove that the resulting method converges almost surely, and this is in contrast to prior works that have only been considering like on average performance analysis. So that's the sort of high-level overview. Now we can get right down to it. Okay, so let's go back to the kernelized expected risk minimization problem. So this is like normal stochastic program, except now we have f of x here. And let's talk about the form that stochastic gradient method takes for this case. It's actually a generalization of the standard method to the functional case. Okay, so we need to compute the stochastic gradient of this data-dependent term with respect to f. And the way we do that is we note that this gradient is itself a function. So this is sort of a gradient, but it's actually a variation or a Fréchet derivative. But that's not too big of a deal. We can still apply the chain rule, and then we note that this term right here is a scalar. And then the question is, what is this function term? Well, we can differentiate both sides of the representer. Sorry, not the representative theorem. The reproducing property of the kernel, which was property 1, and we obtain that this functional gradient is actually just the kernel evaluation at the most recent feature vector. So this is interesting. This says that at time t, the stochastic gradient, which we compute with respect to a training example xt yt, a component of that gradient is just the kernel evaluation at the most recent feature vector. Okay, so now let's write out what is a stochastic gradient given this quick derivation. Well, given that we had this regularizer, that's where this first, let's say, 1 minus eta t lambda coefficient is coming from. The minus eta t lambda is just ft. So the gradient of the Hilbert norm with respect to f is just, the Hilbert norm squared with respect to f is is just f. Okay, so that's this first term. And then the second term is this stochastic gradient term, which by applying the chain rule and the reproducing property of the kernel is just this scalar coefficient and this kernel evaluation of the most recent feature vector. Okay, so here we're defining the first term in that chain rule application as L prime, just for convenience. Okay, so let's note a couple interesting things about stochastic gradient method in the kernelized case that doesn't happen in the normal case. The first is that so our function, which is parameterized by a dictionary of training points, so we can think of that as just a matrix of our past feature vectors at time t plus 1. We just add the most recent training point to our current dictionary. Well, why do we do that? Well, because we know that it's coming into our function representation here through the gradient. And then we have a weight vector, which is it's just the past weight vector scaled by this regularizer, and then the weight associated with the newest training point here is just L prime. So this is interesting. This says that stochastic gradient method is such that the model order of ft grows by 1 at each step and is actually t minus 1. So if we want to take the limit as t goes to infinity, then ft is going to have infinite model order. So that confirms our intuition. So how can we stop this from happening? How can we make sure that mt is much smaller than infinity? Well, let's think a little bit. One thing, so what we propose doing is fixing a Hilbert norm error neighborhood around ft at the current time, and trying to kick out as many dictionary points as we can while remaining in that Hilbert norm neighborhood. And so there are a few different sparse approximation techniques one might use to accomplish this task. The one we particularly adopt is called kernel orthogonal matching pursuit. The reason is it's a greedy method, and these greedy methods have guarantees on their Hilbert norm or approximation error, whereas methods based on convex relaxation, for example, lasso, etc., require very stringent conditions on the kernel matrix, which won't hold in practice. So if we're worried about the error neighborhood, then we have to consider a greedy method. So that's the short story of why matching pursuits. So what does matching pursuit do? Okay, well, we fix an approximation error, and let's sketch a Hilbert norm neighborhood around the current. So sorry, we start at the previous time at ft. We take a stochastic gradient step to f tilde t plus 1. So this is just our stochastic gradient step that we derived previously, and then we fix an error neighborhood around this function, and we try to throw away as many dictionary points as we can until we hit the boundary of the neighborhood. Okay, so there are a couple interesting things to note here. This Hilbert norm neighborhood, we can actually represent it by the span of the dictionary that currently represents our function. So that's thing number one. Okay, thing number two is what is this? What is this dictionary? These DNs are called model points, and they are just a subset of past feature vectors. So we're just keeping a subset of the past feature vectors that are guarantee us to be still inside this error neighborhood. So that's intuitively what's going on. And what we can say by adopting a procedure like this is that the model order at the next time will be less than or equal to the model order at the current time plus 1. So why is this? Well, this would be the result if we just added the full stochastic gradient in, because that would be appending the most recent feature vector to our model. But we're saying, well, let's see if we can find something a little bit smaller. Okay, so that's sort of the cartoon of what matching pursuit, about kernel matching pursuit. So now let's get down into a little bit more details about it. Okay, so on the previous slide we had this f tilde t plus 1. This is just the normal stochastic gradient step that we previously mentioned. Okay, and so we define d tilde t plus 1 and w tilde t plus 1 as the dictionary and coefficient vector updates that would be associated with that stochastic gradient step. And so we just say, well, let's just feed those objects into KOMP until we're at an error neighborhood, or at the boundary of the error neighborhood, and have tossed out as many dictionary points as we can. And so that's the idea here. I'll get to what exactly KOMP is on the next slide. But for now, I'll just want to note that this kind of procedure can be written as a certain kind of orthogonal projection onto a subspace of the Hilbert space. And this subspace is the span of some dictionary and this dictionary is spit out from KOMP. Okay, so here's the gritty details of matching pursuit, and I won't try to parse all of it, but just try to give you an idea of what's happening. So this, so we start with our full dictionary at the current time with our full coefficient vector, and then we find the dictionary element associated with the minimum Hilbert norm approximation error. Okay, and then we check to see if we're inside this error neighborhood, and if we are, then we toss that dictionary point out, and so that's the tossing out, and then the model order decreases. We have an updated dictionary, which is now smaller by 1. And then we have to compute our coefficient vector so that we know what is the decremented function representation. So the result of this kind of procedure is that we have a new function, which is smaller than the initial model order and is in some error neighborhood. Great. So with this kind of scheme presented, we can present our method called Parsimonious Online Learning with Kernels. And so what all it does is, okay, we observe our data stream, we initialize our classifier as a 0 function, and then we do a stochastic gradient step. So here, note this is f tilde, not f. Okay, and then we feed our stochastic gradient step into our matching pursuit subroutine, and that gives us our actual function sequence. Okay, so that's the idea. Now we can talk about how does it actually do. Well, in order to do so, first there are some technical conditions I need to clarify. So we need the feature space to be compact. We need the target domain to also be compact. This allows the reproducing kernel map to always be bounded. we need that. We also need the instantaneous loss to be Lipschitz continuous and convex and differentiable. So this incorporates things like support vector machines with the square hinge loss, but not the normal hinge loss, or for example, logistic regression, or many others. And also, we need the projected gradient to have a finite, projected stochastic gradient to have a finite variance. So note that this is not the straight projected gradient. This is not the straight stochastic gradient. It's the projected stochastic gradient. So it is the descent direction that is defined by the difference between the step we would have taken if we did know sparsification projection and the true stochastic gradient step. Just a technical difference, but these things are almost the same. Okay, so then under these pretty standard conditions, we can prove when we use a attenuating step size and a sparse approximation budget on the order of the step size square that we're converging almost surely to f star. Why might this be a result of, let's say, theoretical interest only? Well, the most important reason is that the sparse approximation budget here is on the order of eta squared, and eta is going to 0 approximately as 1 over t. So that means that the sparse approximation budget is going to 0 like 1 over t squared. So asymptotically, we still might have infinite model order. So this doesn't quite get us what we're looking for. Nonetheless, we can talk about constant step sizes as long as they're initialized to be smaller than the regularization parameter here. Then when we have this constant step size, we can choose our approximation budget to be like the step size to the 3 halves power. And when we do that, we can prove a limit of convergence almost surely. So this is better. This says that we don't need our sparse approximation budget to be going to 0, and we can still learn f star. This is good. We like that. So in particular, this kind of setting with the constant step size allows us to prove that the model order is always finite. And of course, this finite, so that's what this theorem is saying under the same conditions as the constant step size theorem. And the takeaway is that this finite model order, so this constant doesn't appear here, but it determines the worst case bound that the model order may have, and it's dependent on a ratio of the smoothness, or let's say the Lipschitz continuity of the stochastic gradient, the step size we use, and this k was appearing as the constant in our sparse approximation budget right here. Okay. So here's a quick summary of what we know about when we try to do stochastic gradient method in the kernelized expected risk minimization case with this matching pursuit subroutine. Okay, when we have a diminishing step size, we can converge almost exactly, but we need our sparse approximation budget to go to 0 too. This is not good. But when we use a constant step size, then we can converge along a subsequence, but we can prove that the model order is always finite. So intuitively, there's an important trade-off here. Okay. Then an interesting consequence that we have observed from this is that if f star of this is the minimizer of the expected risk with infinite data. If f star is sparse, then even with a constant step size, we'll learn it more or less exactly. So now we can illustrate this this property of our method with an example.
Just to jump in here, so what do you lose by doing this online? If you were going to do this in a batch mode,
at every time. Clearly, the convergence would be at least as good. The model order would be... Actually, I don't know what the model order would do.
The model order would be infinite.
Yeah.
That's the problem.
But so, say you could... Yeah, I guess, yeah.
So
in the limit, it will be infinite.
So suppose you do this. Suppose you do this in batches of, I don't know, 10,000 training points. That's a moderate number. Most laptops could presumably handle that kit for unkernelized logistic regression. Okay, but if you want to kernelize it, which will boost your accuracy because you're now learning a nonlinear model rather than a linear model. Okay, well then now you need a 10,000 by 10,000 matrix computed at each iteration of your optimization algorithm. So that would possibly be that would be a challenge, I would say.
I guess I'm just wondering what I'm not sure. It's clearly not a practical question, but I just wonder what you lose by doing this online at each step, basically.
Yeah, I mean you have obviously a stochastic approximation error, which, as with all stochastic methods, is a non-trivial bottleneck. So obviously, if computation were no issue, you should do Newton's method for sure. For sure, that will work the best. But you might need a quantum computer for that. Yeah. Okay, so now let's talk about an application where F star is a sparse. In order to do that, let's just quickly talk about multi-class support vector machine classification. Okay, so in this case, we have feature vectors that can be of one of several classes. Oh, did I not write the? Okay, they can be one of several classes. Their chalk. That's okay. And there's a class-specific function for each class. So here now F star is instead of being a single F is just a vector output, and it outputs a binary sequence of length C. So it'll have a 1 depending on its classification decision, and everything else should be 0. Okay, so this is just the particular structure of the kernelized multi-class hinge loss. Not that important. This R just denotes that we're making the taking the maximum class conditional probability as our decision, and that's based on. And this is a map from the value of this vector of length C. Okay. So here's just some parameter selection details, but it just says we're using the Gaussian kernel with a small regularizer, a large constant step size, and a approximation budget depending on that step size, and k is like 0.04. Okay, so here's where I mentioned the class details. Okay, so there are 5 total classes. So let's fix a class label. Then the data for that class label is drawn from a unique Gaussian mixture model that consists of 3 Gaussians. So there are 15 total Gaussians because there are 5 classes. Okay, and let's see what happens when we run polk on this kind of multi-class Gaussian mixture model data. Well, we get this very interesting decision surface. These bold black dots are the kernel dictionary elements. These are extracted from the training examples that the algorithm has seen. It's processing them in a streaming fashion, and these curved lines are denoting the class label or the decision boundaries. And so you can see that we end up learning a pretty interesting, like, curvy tessellation of the, or let's say curvy Voronoi-like partition of the space. That's interesting, and also it's pretty accurate, about 97%. So that's good. And here we just do a quick. So how many times do I classify a green as an orange or a blue as a purple? Actually, I'm colorblind, so I'll always classify a purple as a blue. So in this case, the kernel classifier should do much better than me.
Is it cross-validated?
This is right. So this is the right here. This point cloud is the training set, but this accuracy is on a test set. Yeah. So here's just a quick discussion of how this performs as compared with a competing method, which instead of fixing the Hilbert norm approximation error of the stochastic gradient method, instead just fixes the model order of the learned function. So one might note that the descent direction of the optimization method could become arbitrarily biased in a pathological case. This is not a pathological case. Nonetheless, we see that. So this red curve is the competing method, which is fixing the model order, and it does seem to be diverging, whereas we are converging approximately to the minimizer now. We don't know what its explicit form would be, so obviously we can only plot the objective function evaluation over the number of samples. So one thing I should note is that for this approximation error, our method converges to a model order of about of 16. So for fairness' sake, we initialize the competitor with this same model order. Okay, and here's where we are plotting misclassification rate over time. We're seeing that we're pretty quickly getting to near 95%, and there's obviously a lot more engineering that goes on to getting that last 5 that we're still learning. Yeah.
Does small go through larger M's as it converges? Because the final M you say is 16, but do you need any intermediate step where M is larger?
Yes, we do. Right. So, you recall in the third theorem, we just proved that is a finite number, but it could be huge. So, and it depends a lot on the way the parameter selection is done. So, actually, here for this particular experimental run, we do plot the evolution of the model order over time, and we see that we're able to lock onto approximately the right value, which should be related to the number of modes of the joint PDF that generated the data. But unfortunately, for some super complicated data domains, that the number of modes of the joint PDF of the data could be arbitrarily large. If we're trying to predict anything about, I don't know, demographics and human behavior, okay, that should be a really crazy PDF. So the model order could be huge for that problem. And I would be surprised if it wasn't. Okay, so, and actually we're conducting experiments on MNIST hand-digit recognition right now, and we find that depending on if we want to get within 3% accuracy for multi-class, we need model order of 2200. So more complicated models are necessary. It does suggest that maybe we should be composing kernels so that we can take a higher dimensional space into a lower one. But this would be a more principled reason for doing so than the way neural nets come about. Okay, so with that, I can conclude and just say that we focus on this general kernelized expected risk minimization problem for which there wasn't too much that didn't demand a memory explosion of your computer. So that's our major contribution here in the way we way we handle that is through running a stochastic gradient method in tandem with a greedy sparse approximation scheme, and we were able to prove that we solved the problem under some certain settings. And as I said before, our MNIST results are ongoing. So with that, I can take any questions. Polka? Oh, like a dance? It was either that or, like a picture of James K. Polk here. But, yeah.
What would it take to generalize this to function learning rather than just classification? So say I had a generic function from feature space to the reals. And I wanted to do something that looks like Gaussian process, for
that.
something of that nature.
I think that would, let me go back to the original formulation. I think it should be, I think it should just be the way you choose your loss function. So now I think in the case you're describing,
Mean squared error over a domain or something like that.
yeah, like the output y is just some different Gaussian density. So I think it would give you a whole parameterized family of kernelized optimization problems. But if you want to just learn one Gaussian, then you could do this directly by substituting in the negative log likelihood of that density into the loss, or like a function of that, and I think it would work.
And how do you quantify sort of model uncertainty in this setting?
Like, what if I chose the wrong kernel? What do you mean?
Well, I guess you write down, it's more like, I guess it is literally just your loss function. It's your risk.
You could encode that in a few ways by saying that, like, what if my feature vectors are being corrupted by something that I can't measure?
Yeah.
I think there would be a way to extend this sort of approach to that case, and that would handle some form of model mismatch, but not the only form, obviously. Yeah.
This might be a little bit obvious, but so when you're throwing away some of your dictionaries, right?
Yeah, let's go to the cartoon. Yeah.
So instead of looking around a neighborhood of F,
Tilde. Yeah.
instead of trying to be close to where you are right now, shouldn't you be somehow comparing things
With the optimum.
objectives?
Yeah.
And
That's true.
why is that hard, or how does this?
Right. That's fair. So, you could check the objective function value with each different dictionary point and see which gives you the least reduction or something, or sorry, the most reduction. And I think that would work similarly, but somehow that value should be proportional to the stochastic gradient, right? So if you look at the way our error neighborhood is being constructed, the stochastic gradient is just directly appearing there. So I guess these would be alternative approaches, but they might be trying to accomplish something similar.
I'm just thinking about things like Gaussian process regression, where you're trying to learn some function, and you start with a batch of data, and what you're doing is kind of a sequential procedure. You're just marching through the data and maybe throwing away some things as you go along.
Right.
To keep a sparse.
Yeah, the motivation would be to actually be able to do this on an application where you have a data stream, like
Right.
like a robot.
Right.
There's not that much of a coincidence that this is in collaboration with ARL.
So I'm just curious, are there other, a lot of sort of intuitive sparsification ideas which might suggest a nice or initial order of the points to search. What you're doing is just kind of almost picking them randomly, as I understand it, this online. You're not.
Yeah, we just say, okay, we observe this IID sequence, and this is how we should handle it.
Coming in. I just wonder if there might be some way of getting a better sequence of training points.
So like an active sampling type approach.
Yeah, well, you want to get a spread over the space for sure,
Right. I think that would be pretty challenging / intractable to do for the stochastic optimization case or the expected risk. But if I think for the empirical min problem here, there have been approaches like that look at things like the spectrum of the kernel matrix and then drop the dictionary elements associated with low eigenvalues. So that would be one thing you can do. I mentioned in this review, I actually didn't mention it, but it's written here that there are some compressive sensing approaches, and that's exactly that. But those only work well in the offline setting unless they're tailored to the optimization problem. Yeah. I guess with that I can conclude, and I'm happy to take any other questions offline.